Okay, let's unpack this. We're taking a deep dive into an area of engineering that, well, it's often overlooked, but it really dictates the difference between a productive day and a catastrophic accident.
Right.
We're talking about modern machine tool guards and shields. Now, you might think a guard is a guard, right? But the sources we've gathered show these systems are incredibly sophisticated.
They really are. It's not just about, putting up a barrier. Our mission today is to understand how these highly engineered solutions tackle this huge, expensive industrial paradox. Well, how do you ensure the absolute non-negotiable safety of an operator against some really severe hazards, while at the same time maintaining full visibility, accessibility, and keeping production efficiency high?
That's the tension, isn't it? That safety versus speed idea. That defines the whole challenge.
It does.
So before we get into the specifics of each machine, what are the core universal hazards that these guards are engineered to solve across, an entire shop floor?
We can pretty much categorize them into three main physical threats. These exist wherever you're shaping or moving material.
Okay.
First, there's direct contact with the actual cutting tools or abrasive surfaces.
The obvious one.
The obvious one, yeah. Second, rotating components. So think chucks, spindles, drive shafts, anything that can cause entanglement or contact risks.
Right.
And third, the really unpredictable danger of flying material. That could be hot chips, coolant spray, or even whole parts being ejected.
And the scope here is just massive. I mean, we are looking at solutions that have to work for a high-speed CNC machining center just as effectively as they do for, say, a heavy-duty hydraulic press that's supplying hundreds of tons of force. The engineering has to be so adaptable.
Precisely. And the key design philosophy that runs through all the source material we found, this goes for everything from a simple drill press shield to a complex mill enclosure.
What's a common thread?
The common thread is that safety cannot compromise the actual operation. It can't get in the way. That's why you see these tailored barrier systems, transparent shatter-resistant panels, secure enclosures, and this is critical interlocked access doors that shut the machine down if the guard is breached.
Because if the operator can't see what they're doing.
Exactly. If they lose sight of the work, or if the guard makes setting up a job take an extra 20 minutes, compliance just plummets.
And that defeats the entire purpose.
The entire purpose. So the guard really has to be a functional component of the machine, not some annoying accessory.
Yeah, that makes sense.
It has to be. The moment an operator sees the guard as an obstacle, they're incentivized to bypass it or remove it. So the best safety solution is one that is virtually invisible to the workflow until that moment it's critically needed.
Okay, let's talk scale then. The sources gave us this really comprehensive list, which drives home how specialized these systems are. We're looking at customized solutions for, well, everything. Manual and CNC mills and lathes, radial arm drilling machines, drill presses, then you've got high-force equipment like shop presses and power shears.
Yeah, big stuff.
All the way to finishing machinery, like grinders, sanders, and bandsaws. It's a huge range.
And that breadth of equipment means the hazards, while fundamentally similar, are expressed with wildly different energies.
How so?
Well, on a CNC mill, you've got incredible rotational speed and high-velocity chips flying everywhere. But on a hydraulic press, you're dealing with immense potential energy that, if it's released catastrophically, needs to be contained almost like an explosion.
Wow. So even across these really different machines, we found that the general hazard prevention approach is pretty consistent. It goes beyond just preventing, direct physical contact with the sharp and spinning parts.
Right. There's a huge emphasis on managing pinch points.
And pinch points can be deceptive, can't they?
Very deceptive. They often don't even involve the cutting tool itself. It's more about the interaction between moving parts like a vice jaw closing on the table or the ram of a press descending.
Okay, I see.
These are often slow, high-force actions. The guards have to be robust enough to withstand accidental contact, but still flexible enough to allow for loading material.
And then there's the issue you mentioned before, the ejected material. That seems like maybe the most difficult challenge because it's so unpredictable.
That's where material science really steps in. I mean, think about it. When a tool bit shatters or a piece of stock fails at several thousand RPM, that small fragment becomes a high-velocity projectile.
Like bullet.
Literally. The containment system has to absorb that tremendous kinetic energy without failing, or worse, sending secondary shrapnel inward toward the operator. It's a literal battle against physics.
Okay, we've covered the general approach, but here's where it gets really interesting. We can actually zoom in on 8 specific, tailored solutions from the source material.
Yeah, let's break it down. We can organize them logically, starting with the heart of rotary machining equipment.
Let's start with the workhorse of any modern shop, the manual and CNC mills.
Right.
For mill guarding, the protection is pretty clear. Shielding against flying chips, coolant spray, and of course accidental spindle contact.
Hey.
But the standout detail, the real engineering insight here, was the installation.
The no drilling required feature.
Exactly. The use of a CNC machined aluminum guard that requires absolutely no drilling for installation on mini vertical mills.
And that no drilling feature is a phenomenal insight into what you might call compliance engineering.
What do you mean by that?
Well, we found that the greatest friction point in safety compliance isn't always the cost of the guard, it's the implementation time. It's the downtime you need for installation.
Ah, so taking a machine out of service is expensive.
Hugely. So this design directly addresses that friction. You're turning a job that might involve hours of drilling, tapping, and realignment into a 15-minute bolt-on operation.
And that immediately raises the likelihood that people will actually do it.
Correctly and quickly, yeah. It's an efficiency feature disguised as a safety standard. It's brilliant.
That's a great insight. Okay, shifting to manual and CNC lathe guarding. Here, the sources really emphasize the material itself, shatter-resistant ATS guarding. Why is that material choice so critical for a lathe compared to, say, a mill?
Well, lathes pose a really distinct kinetic threat because of the rotational mass that's held in the chuck.
The workpiece itself.
Exactly. If that workpiece or a fixture or a tool fails while it's spinning at high RPM, the shrapnel has incredible energy. So the sources specify ATS, that's aramid thermoplastic sheet, because it's engineered to handle that massive localized kinetic impact without breaking apart.
So it won't send fragments through the panel.
Right. It's a high-consequence containment scenario. And that specialized transparency means the operator can watch the precision cut happening, but they're safely contained. It's not just transparency. It's high-impact optical clarity that can withstand extreme stress.
Got it. Okay, moving on to radial arm drilling and drill press guarding. These machines are everywhere, often used for quick, repetitive work. What are the specific threats being neutralized here?
The primary hazards are a little different because the operation is vertical and often more manual. You're protecting against the very real danger of entanglement with the rotating spindle.
Clothing, gloves.
Yeah, things getting caught and pulling the operator in. You also need robust shielding for pinch points from the moving quill and drill head, and of course, protection from debris. The guards here are usually durable and adjustable, often like a clear cage that surrounds the chuck and moves up and down with the drill.
Okay, so we've covered systems driven by rotation. Let's shift to hazards defined by just sheer brute force, high force, and cutting equipment.
The risks here feel inherently high consequence because the failure point is often explosive.
And that brings us to hydraulic shop press guarding. The enclosure here does the standard work, shielding operators from crutch hazards and ejected parts. But the sources underscore a really unique requirement: containment of high-pressure failures.
What exactly is a high-pressure failure in this context? Is that like a hose bursting?
It could be, yeah. We're talking about a component or fluid failure under immense pressure. A hydraulic line ruptures, a fixture fails. The energy released is tremendous and instantaneous. It can turn small metal components into shrapnel moving faster than a handgun bullet. So the guard isn't just designed to block slow movement. It has to be a robust, high-energy absorption enclosure. It has to contain that catastrophic event.
That changes the whole design requirement from just a shield to a full-on containment vessel.
It really elevates the stakes. Okay, next up, power shear machine guards. These are for cutting heavy sheet metal. Here, the sources specify dual protection: front and rear shear guards. Why both? The front seems obvious.
Yeah, the front is for blade contact, but the rear is critical because sheet metal cutting produces highly energized scrap and cutoffs.
Wow.
The rear guard is necessary because that cut material, especially if it's thin or curved, can be ejected backward at high velocity. Or even more dangerously, it can ricochet off something in the shop and create a secondary projectile hazard that a front-only guard would completely miss.
That's a great point about secondary hazards. Now, for more general cutting, we have vertical and horizontal bandsaw guarding.
Bandsaws present that classic productivity challenge, don't they? You need to constantly adjust them based on the material, the shape, the angle of the cut.
So what's the design focus?
Adjustability. According to our sources, it's all about adjustability. These guards have to shield the blade hazard completely, exposing only the minimum necessary cutting section.
While still allowing full cutting visibility.
Exactly. And if that adjustment isn't user-friendly, the guard just gets locked in one position or, taken off altogether.
Which defeats the whole purpose.
Precisely. If the guard itself forces the operator to make an unsafe compromise just to finish a cut, the system has failed. The engineered solution has to move with the operation.
Okay, finally, let's wrap this section up with abrasives and grinding equipment guards. These machines create a totally different type of hazard. Not big chunks, but high-speed fine particles and heat.
For adjustable belt and disc sander shields, the purpose is clear: protecting operators from the abrasive wheels and the fine, hot debris. And for this kind of precision work, visibility is just paramount. If the guard material scuffs or clouds up quickly from all the particle bombardment, the operator loses that visual feedback, productivity drops, and again, you get that incentive to bypass the system.
And the ultimate goal seems perfectly summarized in the requirements for surface grinder guards.
It really is. The design goal listed is improving safety, visibility, and compliance without sacrificing access or productivity. That is the mission statement distilled.
Right.
Surface grinding requires precise, continuous access and often very close work. The guard has to allow that access while keeping intense heat, fine grinding dust, and rotational hazards fully contained.
This specificity, this whole idea that you can't just swap a shear guard for a grinder guard, it just shows why the tailored approach is so critical.
It completely shifts the focus from safety as like a generalized regulatory burden to safety as a highly engineered, machine-specific requirement. The little engineering details, whether it's the no-drilling installation for the mill guard or the shatter-resistant ATS on the lathe, they prove that effective safety has to actively reduce the setup friction and downtime. That's the synthesis here. Safety that's difficult to use is safety that is inherently compromised.
And when we connect this back to the benefits for both the facility and the operator, you realize these are sophisticated operational enhancements. They achieve compliance and efficiency.
Right, by improving visibility, guaranteeing tool access through intelligent design, and just fundamentally reducing hazard exposure. They turn accident liability into predictable, integrated workflow reliability.
And that reliability is often enforced through interlocks, right? Systems where the machine literally cannot run unless the guard is correctly secured.
Exactly. That takes the safety decision out of the operator's hands during the actual cycle. It provides inherent protection and compliance assurance for the whole facility. Integrating safety into the machine's own operational logic is really the final essential step.
So what does this all mean? When you put it all together, the main takeaway seems to be that modern machine tool guards are far from simple barriers. They're highly sophisticated, tailored systems.
Yeah, they're designed to manage specific energy and material challenges across this incredibly diverse fleet of equipment, ensuring containment with crucial operational visibility.
And the fact that durable guards for high-precision equipment like surface grinders explicitly prioritize compliance without sacrificing productivity, that just raises an important question for the industry, doesn't it?
It really does. Why is safety so often framed as an obstacle or a hindrance to production when all the engineering evidence we just reviewed shows it can be a fundamental enhancement?
Something seamlessly integrated.
Right. The specialized nature of these solutions proves that the only way to succeed is to meet the machine where it is, addressing its specific operational hazards, not just some general idea of risk.
That leads perfectly to our concluding thought for you to mull over. Given this universal emphasis on transparency, on shatter resistance, on full visibility in all these modern guard designs, how much does the operator's immediate visual feedback of the machinery, being able to see the danger safely contained, how much does that affect their overall sense of trust in the system and, as a result, improve their long-term compliance behavior?
That's a great question.
That balance between the engineered containment and, human psychology, that really seems like the next frontier in shop floor safety.